Buildings are complex structures made of numerous building products and on-site labor. Whilst materials are essential for that, we rarely compose buildings directly out of raw materials. We fabricate them using standardized materials like brick or steel beams, or components like doors and windows that are manufactured from multiple commercial materials, or finally assemblies that are complex configuration of components. The facade is an example of an assembly. It comprises of different components or systems, such as windows, shading devices, structural elements, control system, and so on. Following this taxonomy, the component scale is therefore allocated between material and building scales. Components are not monolithic and uniform building parts. Think, for example, of a window and the many different elements it comprises of. So, in order to better understand and manage circularity at component scale and by extension to assembly level, we should first try to identify all the elements the component consists of, their functionality and their interfaces. And we can do that by carefully identifying the separate parts that make up the component. For the window, that would be the window frame and the several hidden parts within the frame, but also the glass pane, the heatings, the fittings, and so on. Design is central and can be seen as enabling for circularity. For example, we can design the window to be able to take apart. However, unless there is a company to collect the parts and reuse or recycle them, the components are not circular. And there needs to be value for the company to engage in such practices, economic or other. A financial concept or a business model to enable that, including all involved stakeholders, is essential. And the business model also needs to make provision and manage the recovery of components as an integral part of its operation. For example, establish the adequate facilities for processing and storage and install a technology to track those resources. The example of the window exemplifies that all aspects are interlinked and need to work in synergy to realize the circularity potential of a component. Making a component more circular means thinking of all aforementioned aspects and developing a comprehensive understanding of how they interrelate. We can try to optimize the circular performance of components using key performance indicators, also referred to as KPIs, that focus on material input and output. These KPIs can help us identify where the materials that we use are coming from, and if we have designed our components in a way that the resources can be recovered. Some frameworks, considering the whole life cycle, are useful to provide such indicators. Life cycle assessment, or LCA, can be a useful methodology to understand the impact of our components. Based on LCA, we can look at indicators like the global warming potential of materials, fossil fuel energy or renewable energy for the production, recycled and reused materials content, or resources out of the components at the end of the life cycle. Such indicators relate, of course, to design decisions, but also point to the link with other aspects. For example, the use of renewable energy is a technology that can be integrated in the design. However, to make it feasible, in most cases, the production of renewable energy requires selling this to the network, so it becomes a business case that needs the right stakeholders. Or the indicator about recycled content. This depends on the selection of material, but also, in the end, the specific material supplier and product manufacturer. Similarly, Levels is another framework consisting of core sustainability indicators for buildings, commonly used in the European Union. Levels provide additional indicators such as durability, bill of materials, and demountability. Finally, the R strategies also prescribe a set of indicators to consider in a component's design and operation. Following the R strategies objective, more nuisance indicators or other guidelines can be established, such as modular or low-tech design. Furthermore, the establishment of a financial concept, the involvement of the right stakeholders, and the identification of the input and output of resources. To conclude, here are some key points to take away for designers and suppliers of building components in order to promote circularity in the built environment. First comes minimizing resource input, waste, emission, water, and energy leakage. Furthermore, slowing, closing, and narrowing energy and material loops, particularly during the operation phase. Finally, at the end of life, avoiding disposal and loss of economic and ecological value. Design for disassembly is key to enable those strategies. However, additional aspects related to economy management and stakeholders need to be considered for a comprehensive thinking of components' life cycle.